Hi, my presentation will be about Richard M. Karp, and I'll be going over quickly some of his contributions to computer science through his creation of several algorithms. To start, we're going to quickly go over a little bit about Karp. He was born in Massachusetts in 1935, followed by three younger siblings. He would actually follow in his parents' footsteps, attending Harvard, where he graduated with his bachelor's in 1955. Not only stopping there, however, he'd go back to Harvard to not only get his master's, but also his PhD in applied mathematics. He later joined IBM's research staff in 1959, where he'd create a few of his famous algorithms, but it wasn't until he would become a professor at University of California, Berkeley, where he'd make a bulk of his algorithms in collaboration with others. As mentioned earlier, Karp's large contributions to computer science stem from his cooperation with others to create algorithms. Within 1962, him first solving the famous traveling salesman problem with Michael Held, using matrices between cities, being able to create an algorithm that would be able to give an answer in exponential time. Another one of his famous algorithms he developed in 1971 was the Edmonds-Karp algorithm that he made in collaboration with Jack Edmonds. The algorithm solved the issue of maximum flow in a flow network, where a real-world example might be something like a company trying to ship a package, which the package would represent the flow, from Los Angeles, which would represent the source, to New York, which would represent the sink, using trucks to transport in between cities. If there is only one truck for the route connecting the pair of cities, and the truck has a maximum load, then the algorithm would be able to give us a maximum load it can transport between the cities while also considering all the other cities. In 1973, Karp developed the Hopcraft-Karp algorithm in collaboration with John Hopcraft, where the best way I could describe it is something like there being a limited number of slots in whatever you can think of. So let's say like a hotel or jobs that people are applying to. But these people that are applying to these jobs or trying to get these hotel rooms also qualify for multiple of these slots. What the algorithm will actually do is do its best to assign as many people to these slots that they can qualify for on like an actual bipartite graph. Continuing with his notable work, Karp in 1980 developed the Karp-Lipton theorem, which proved that the Boolean satisfiability problem, also known as SAT, says that if a problem can be solved by Boolean circuits with a polynomial number of logic gates, then the polynomial hierarchy will collapse to its second level. But what's actually important about that is that the theorem is used for the idea that for every problem whose solution can be quickly verified, that same problem can also be quickly solved. This being the P versus NP problem, but identifying as NP completeness, which we will go over more here shortly. And finally, in 1987, he created the Robin-Karp algorithm, which, with a quick summary, uses hashing to find patterns in strings, which a good real-world example might be something like image back searching using hash values. But that's one of the several applications for the algorithm. With more specifics, we will actually also go over momentarily. For his contributions to the theory of algorithms, he was awarded the Turing Award in 1985, where they listed his works and contributions to NP completeness, creation of efficient algorithms for network flow, and the identification of polynomial time computability with the notion of algorithmic efficiency. But how is all those algorithms actually impacted computer science? To start, his Edmonds-Karp's algorithm used to find the maximum flow in a network graph, or the one I used the truck example in, has helped in optimizing routes, solving scheduling problems, and finding the shortest path between two vertices, which, when relating to computer science, has had a drastic impact on how packets and computer networks will actually flow, making the rules for how to transfer data much more efficient. Another example is the Karp's Robin-Karp algorithm has allowed programmers to create plagiarism detection technology to be able to push for more responsible education. And the final large impact I will be going over is identification of polynomial time computability, leading to him identifying NP completeness. A pretty basic summary of NP completeness is that a problem, or P, in NP is NP completeness if every other problem in NP can be reduced to P represented by polynomial time. Because of this discovery, it has played a pivotal role in the study of algorithms and computational complexity, especially in the realm of artificial intelligence. Today, Karp is 89 years old, working as the founding director at Berkeley at the Simons Institute for Theory of Computing, where he leads his group of scientists to researching more algorithms focusing on bioinformatics. All right, that is all. Thank you. And here are my sources if you need them.